Alrighty, we're back. So took a bit of a break between this video and the last video's recordings. So in the last video, we talked about the run scrape deck pipeline, which kind of explains the code and things that I used to get replay JSONs from the replays, the Zoombook replays themselves. And for this video, we're going to be talking about the deck type model. Okay, so after recording some of the past few videos here, these videos are very technical. And so what I think I'm going to do is I think this video that goes over the deck type model is going to be very important for people to know once we get into the Word League analysis notebook. And so what I want to do here is I actually want to recommend this video, deck type model, and the format Word League analysis videos for even non-technical people. All right. So with that said, if you were following along with the previous videos that were really technical, I'm going to try to, make the wordings and make everything like a lot less so. So, hopefully I could get people to follow along. And the reason is, I think understanding what went behind this deck type model, what to expect from it, its strengths and its weaknesses is going to be really important because we're going to be relying on this deck type model once we start trying to do analysis across deck types, right? Chaos Turbo, Warriors, all that. So I want to say everything that I did during this process, and I'm going to try to make it, a bit more friendly to non-technical people. But at the same time, I kind of brushed over the notebook just now, and there's going to be some, spots where it's going to be kind of unavoidable. So just a little heads up, and this might also be a pretty decently big video as well, because I'm also going to be covering this deck model demo part as well in this video. Originally, I think I was going to have it split, but this is a separate notebook that kind of extends from this one. Just going over a deeper dive of the performance of the model, why it performed the way it did, stuff like that. I'm going to include that in this video. All right, with that said, let's start. So, go to format deck classification model. So we're going to build an XGBoost model to classify go format deck arc or deck types using main deck data from top tournament performances. So, first and foremost, I had to build a deck type model. And the point of this model is that it's going to be looking at cards from the main deck and trying to predict what those cards, what that deck type is. So this model were to see like Chaos Turbo, Chaos Monsters, Flips, all that. You might want to predict that this thing is Chaos Turbo. That's what this model is responsible for. Looking at cards or features and making that prediction of the deck type, or it's going to be called deck class here in this notebook, just because of some. I had to use deck type for another column actually, but when I say deck type, I also mean deck class, so it's kind of interchangeable in this notebook. Okay, so that's what the model is supposed to do. And I'm making this model because originally my plan was I was scraping data from the Worley Excel sheets, right? And in the Excel sheets, there's a sheet there that has deck history, deck usage history. Let's see if I could actually let me pull this up actually. So tinyurl.com. So you might recall when I had that Excel pipeline video that the things that we scraped were the matchups and films that has the replays and the war matches, and also the deck usage history, where I could actually get the deck types directly from the sheet. And it would be ideal to use this instead of using a model because these were manually verified, right? Or mostly manually verified. So it would have been ideal, but some of the things that I noticed when trying to scrape from the sheet, at least in season 1, is that there's a lot of weeks that was missing in the data. And also, one of the main things that I needed to work out when trying to join these deck types with the matchups films is that I needed to join by the players' names. And even after cleaning the names and making everything as consistent as possible, sometimes there are typos that people just manually did between the players' names on here and on the deck usage history that made it so that there would be missing data because the joins, player names, weren't consistent. So there was a mix of things that I noticed when trying to scrape data from this Excel sheet for season 1 that I thought, it might be more convenient for me to just make a model. Okay. And also, because with deck usage history, you can kind of see here, like jar CT and, I think it's also Decree, Chaos Control. I would also have to clean these deck types as well, even if I had them, and say like, Decree Chaos Control is Chaos Control, jar CT. I'm guessing this is just Chaos Turbo with jar greed, right? I would have to do some manual work anyways on top of already trying to join these things and doing whatever cleaning was necessary. So the TLDR is I couldn't just use this because I would have a lot of missing data. And I saw that up front when trying to work with season 1. So I went ahead and built a classification model here. And we're going to talk about that process. So let's kind of get started here. All right. All right, cool. So this is a publicly available notebook in the repository that I shared. The notebooks, basically, they're rendered markdown files, which basically means they're kind of like a book, I guess. They have, I have a table of contents on here. They have chapters and all that. So you could, look at that rendered notebook. It'd be a lot more friendlier to read than just code. All right. Although code is also included in this notebook. Okay. So let's actually just break down what we're going to be covering. So we're going to do some setup in the beginning. Then we're going to do some data loading. So this is also a part of the setup, some processing, stuff like that. Then we're going to do some exploratory data analysis. And what that means is to train a model to do predictions, we need to give it training data. So where am I getting this data from? I'm getting it from format library. I made a video a few videos ago or it might have been last video. I don't recall. But I made a video where I covered a scraped deck pipeline where I scraped Yu-Gi-Oh decks from format library. All right. I think I have like 1,600 decks. Okay. So those are the decks that we're going to be using to train our model. And that's also the benchmark that we're going to be using as well, because I had the assumption coming into this that the standard of format libraries labelings would be acceptable for my model as well. So it was just something that was convenient, is already labeled by format library. There's a decent amount of samples over there, 1,600 decks, and I'm just going to scrape that and use it to train my model. So that's our training data. Now we're going to do some, exploratory data analysis or otherwise EDA on it, because depending on where I got this training data from, there's going to be some biases with it. For instance, these decks from format library are top decks, right? They're top performing decks from events, right, in format library. What that means is you're mostly going to see deck types that could top, right? So you're going to see very low. You're going to see some heavy class imbalances when it comes to decks that you might see in tournaments or you might see in the World League, but just wouldn't really top. So we're going to look at some of the biases with our training data, and just do some analysis on that, and also just some information about our training data in itself. Then we're going to do some quality stuff here on the data, just to, because there's some things that we notice in the data as we're doing this EDA that we could fix, and we'll talk about that when we get there. And then we're going to go down to the model development. So this is kind of the whole pipeline that we're going to be doing to, train our model, test the model out of sample, gauge its performance, tuning, and then, just some stuff along those lines. All right. And after that, that'll be the end. We have to save the model. And then after this notebook, I'm actually going to do an extension of this model development process with another notebook where we analyze the performance a bit more, why it performed the way it did, essentially. And the way that notebook's going to be laid out is basically through examples. And I think, let me actually talk with this first, and we're going to actually pull that up as well. So deck model demo. So here's the table of contents for this second one, and more or less, we're just going to look at the examples they looked at where our model didn't predict correctly. And we're going to look at those examples and see if there's a pattern as to why that happened. Okay, so that's kind of the summary of how this is going to go down. So let's kind of start from the top here. So some setup, don't worry about this. Load in some libraries, essentially, just getting things prepared for everything. We're going to pull in this data from format library. If you don't recall, in the scrape deck pipeline video, this is the data that I've scraped from format library and how I've structured it. So we can actually take a look at that right here. Let's see. So this is the table. All right. So we can see here, I got this from format library. So we got the publish stat, we got the deck type, whether it's a main or a side deck. The deck category, if you're familiar with how format library displays its data, this would be like aggro, control, burn, combo, stuff like that. Then the deck class, otherwise also known as deck type. This would be like warrior, chaos turbo, chaos control, all that. The card name, the card amount or the ratio, so it'll be between 1 to 3. The deck builder, the event name, event placement, and the URL of the API endpoint with this data. All right, cool. So that's the structure of our event decks data. You can also look more into that in that deck scrape deck pipeline video. All right, cool. So we're just bringing in that data here, and we're also filtering for only main decks. We're not going to be messing with the side deck here. Okay, so these are main decks from Format Library, and there's 45. I mean, there's 1,600 decks. We'll look at that in a bit later. So some initial processing. This is just some cleaning steps. Don't worry about it. Okay, we're also going to change the formatting of some of these values. Also, don't worry about this. All right. And then also, I ended up creating a separate data frame. So the data that we just loaded in from the database is called event decks. That's the data that I've just showed you, the table that I've just showed you. And if you recall from event decks, what's kind of happening there is there's many rows of data that is of one deck. So for instance, you can see here that this Dueling High deck that placed number 1 at PWCQ 73, there's a row for all the cards in his deck, right? So the rows is equal to the number of unique cards in his main deck, where the actual ratio of these cards are in this card amount column. Okay, so there's multiple rows for per deck. All right. All right. So with that said, that's the event decks data frame. That's what I just showed you. In this, I'm also making this other grouped event decks data frame, which honestly don't worry about it. But we're going to be using both of these data frames to get to the EDA section of this notebook. All right. And here I'm just kind of going over each column in the event decks data frame, just kind of talking about what I kind of just described already, what each column means and all that. All right, cool. So again, another snippet of that event deck data frame that we just looked at. So this is actually of one specific deck, right? It's that Dueling High deck. You can see here that its dimensions, it has 29 rows. That means there's 29 unique cards in this deck, all right? Cool. And then here's that second data frame I made. Basically, what it is that I removed the cards from the cards columns from this data frame. And what this actually is that now each deck is only a one row, right? So this one row here, the same deck that we just seen here of Dueling High's PWCQ deck is actually just one row here, where this deck class is Warrior, Builder, event name, event placement. I had to make this other data frame to make some of the analysis easier later on, but it's not very important to know. It's kind of describing what these two data frames are that we'll be messing with a bit later. All right, so now we're getting to the EDA section of the notebook. So we're just going to kind of look at the data, what we have, basically. All right, deeper dive into these data frames to get an understanding of what's going on, what's going into our model. So first of all, so these are topping event decks from Format Library. So what kind of events are we talking about here? So how many series do we have? How many events and topping decks, all that. So this chart right here shows the number of Go format events by series. So the PWCQ example you just saw was number 73. And we can see here that of this series of PWCQ, it actually is the most frequent series in our dataset. So PWCQ, we got 63 events from PWCQ in our dataset. All right. Second most is FOC with 36, Obelisk, GFC, so on and so forth. Something that's a bit interesting is that these series are colored or filled by the number of top decks from those series. So what that means is that you can see here that Obelisk might have more events than GFC, but Obelisk is a lot smaller in tournament size. So I think Obelisk brackets might be like 8 people brackets. And so a topping for Obelisk might be like top 4 or something. And so you get a lot less top decks from Obelisk than you would GFC, because GFCs, there might be like top 32, top 16. So you're getting more tops per events in GFC than Obelisk. So that's just something kind of convenient to know of the distribution of, where these decks are coming from. Okay, then here's also a distribution of the event placements from our decks as well. So we can see here that, most of our decks topped somewhere between 0 and 5, and then it can go all the way down to 32. So top 32. And of course, tops are proportionate to the number of participants in these events. So here's also the stats on the placements of our decks. So the mean is about 5, the minimum top 1, and maximum top 2, median top 4. All right, cool. All right, so now we're going to do some deck analysis. This is just further EDA, but we're going to be looking at deck types and cards and stuff like that now. All right, instead of just looking at events. So let's look at the deck types. So this first chart is deck classes. So this is from our training data. How much are from these classes? So the number one class deck class in our data set is Chaos Turbo, of course. There's 623 Chaos Turbo decks in there, like 1,600 decks. Second most popular would be Warriors, 250. Then Go Control, Chaos Control, so on and so forth. And you can see that there's a lot of deck classes in our data set. But you can also see how the deck needing to be a competitive deck and needing to have some kind of popularity as well is affecting its sample in the dataset as well. For instance, we only have 2 empty jar decks, right? All right. Cool. So that's the breakdown of the deck classes in our dataset. And the point of this, I guess, to just kind of rehash it, is that there's a, again, bias to very competitive decks. We can see that, with the top being what it is and the bottom being what it is as well. All right. So year by year breakdown. So now we're actually going to look at the years from our data set. So the lowest is 2005. And we can see that the number one most popular deck type in 2005 is Go Control with 40 decks that topped. All right. Go Control, Chaos Zombies, so on and so forth. Then 2018, we got Go Control, but very few events, right? Like the highest number count of deck class in 2018 is Go Control with about 8, right? Then Chaos Turbo, Control, so forth. Then you got 2019. Likewise, the number of samples per deck class is very small this year as well. So the highest number is 10 for Chaos Control, Go Control, and obviously the order of these deck classes is changing as well as the meta is kind of changing. Then you got 2020. You start seeing a lot more events here. Highest deck class here is 30. You got Chaos Control, Chaos Turbo starting to get in there. You got Go Control, Chaos Warriors, right? Then you got 2021. All right, so this is where Chaos Turbo kind of took over. And then you see Chaos Warrior as well. Chaos Control, Warrior, Panda Burn. 2022, this is when you start seeing the meta shape the way it is right now, where you have Chaos Turbo, Warrior, Chaos Control, Panda Burn, Go Control. And then you can also see from 2022 and onwards, the number of decks per year ends up being a lot more, right? So we have over 150 or 150 for our highest deck class sample here. Then you got likewise 150, and then 2025. I'm not sure. We're kind of earlier in the year, but currently we're at like 30 decks. Okay. All right, cool. So deck size distribution. So how many cards are in each deck? So we're looking at each deck and we're seeing how much cards are in each of them. So we would expect the majority to be 40 card decks, but sometimes there are 41, 42. And apparently we have some decks in our data set that have 80 cards, right? So, that brings us to our next section here about data quality. So if you've been following along, you may have noticed that there's some irregularities with our data. So we're going to be looking a bit closer at these irregularities and see what's going on here. So number one, card count. What we've just seen is that the number of cards per deck could go up to 80, right? Not legal. Should be between 40 and 60 on Dueling Book. So these 80 card decks, we're going to take a look at them and see what happened. So in the last section, it's great to see that there's no deck with cards below 40, so it's great to see that as well. But there are also decks with over 60 cards. So there's only 5 cases of this. And I looked at each of them. And when I did, on Format Library, it looks like it's 40 decks. And when I checked the API as well, it's saying 40 decks. So maybe something with the scrape that caused it maybe to, maybe there's a duplicate for this deck perhaps. But anyhow, we're going to be filtering these cases out anyways because it's only 5 and it doesn't really matter. So we're just going to take those out. So each deck here has, so in Format Library, it shows as 40. We have 80. Doesn't really matter. We're just going to remove them from our data set. All right, just to make sure that we're trying to make the data as clean as we can. So next is label verification. So if we recall a bit earlier when we looked at the different deck classes in our data set, this is actually quite a bit, over 50, right? And some of these down here might look a bit weird, right? You have Goat Burn, Gravekeeper Burn, Crane Turbo, right? You got Jar Turbo, and you got Empty Jar, right? You got You got some deck classes here that might make more sense to be labeled with other deck classes together. And we'll talk about what that means in a second. So in label verification, when we looked at all the deck types in this section, there were some deck classes that were very similar. For example, Chaos Warrior Turbo and Chaos Warriors, or Jar Turbo and Empty Jar. I've also seen Zombie Turbo and Zombies. So let's take a look at them and see if they can share the same deck type. The reason this matters is to reduce dimensionality once we start modeling. We don't want to lower our precision because the model can't decide between irrelevant differences. Okay. So the first thing we're going to look at is Chaos Warrior Turbo. What is this? Is it much different than Chaos Warriors? Stuff like that. And when I filter for Chaos Warrior Turbo in our training set, we have 11 occurrences here. And just looking at the players' names, I could kind of tell what this deck is. Mostly it's from Pikatron as a more recent, but at the beginning it used to be from the Nano. And so what this deck looks like is actually these decks with Warrior Package, Thunder Dragon, Breaks, something like this. And I think this is distinctive enough from Chaos Warriors and Turbo and so forth to be its own deck type. All right. So that looks fine. After looking at these examples, it seems that Chaos Warrior Turbo are those nano-like decks with a Warrior Package and Thunder Dragon. Distinctive enough, etc. Alright, so next, let's take a look at Empty Jar and Jar Turbo. So we know what Empty Jar looks like, but what the hell is Jar Turbo? Apparently there's only one occurrence of it, and it's from James Ark. So if you look at this deck, it kind of looks like a heavy slump deck. It has these Taiyus and these jars, and it's also taking one heavy slump, but maybe it might not be classified as heavy slump because it doesn't have more copies of slump. It's not as core of a card in this deck. So there's something going on here, and I guess it kind of is what it is, but at the same time, the sample is just one anyways. So it's going to be filtered out regardless, but there's only one occurrence of this deck type, which means that it doesn't really matter to go over since we'll need to filter them out later for the model, because the model needs a lot more sample because we're going to be doing a train and test split of the data. We'll talk about that when we get there, but basically we need at least 5 samples. However, this example from James seems pretty similar to the heavy slump deck type. Now, let's take a look at Zombie Turbo versus Zombies. So this is Zombie Turbo. I think this first deck looked pretty similar to just regular zombies, right? This could pass as a regular zombie deck, in my opinion. And the second one here, this one was a bit interesting. I kind of see how this could be labeled as a Chaos Turbo deck, a combo deck. That's what it's calling it. There's a lot of combo elements here with forgot card to safe return and all that. Cool. All right. Personally, these Zombie Turbo examples are distinctive enough with regular zombie decks to have as a separate deck class, mostly referring to ATJ's deck. The zombie deck type itself is too varied to distinguish beyond the zombie monsters. Is what it is. All right. All right, cool. So we looked at some of those examples where I've seen deck classes that seem similar. I looked at them and I could kind of see why they might be separate from, another deck class I want to lump it in with. At the same time, the rest of the examples I want to look at was at a low enough sample that it wouldn't matter anyways because they would get filtered out during the modeling process. So I kind of just skipped over the rest of the deck classes that I went over, and we're just going to hop into the next section here. All right, so edge cases. So originally, I was going to go over the decks with small samples since these are primed for mislabels. So there's apparently a Crane Turbo deck in our dataset, and when I looked at it, it was actually mislabeled as a Chaos Turbo deck. And there's also this deck type called Udder in our data set. And when I looked at them, there were actually Chaos Turbo decks as well. So, just some mislabelings that I saw with lower sample deck types. Decks that are before the modern era, for example, those decks in the 05, they also don't have very relevant data for today's usage that I would also filter these decks out. So what this chapter is basically about is that I'm going to be starting to clean the data now for things that I don't want to put into our model. So this is going to be a combination of removing those decks with high card count, removing decks that are too old, stuff from before 2018. I'll be removing those. And also I think I'm also going to start removing, I actually have it listed out here. So we're going to filter for deck classes after 06. We're going to filter for deck classes with a sample greater than or equal to 5. We're also going to filter out the decks that has 40 cards in the main deck. All right. So that's what this section is about. We're just going to clean the data once and for all here into this one data frame model data. So now we kind of tried to do some, surface level EDA on the data. We got a bit of an understanding of where this is coming from, some of its biases. We looked at the deck class distribution. We saw, which deck class was our training data mostly composed of, which ones weren't. We try to see if we could spot mislabelings in the lower samples, or just class names that look similar. And I don't have them all listed out here, but of the ones that I looked at, they look fine to me. I've dealt with it. All right. So all that said and done, we now have our more or less clean data frame here of model data. All right. Cool. So that was the EDA section. We got all that done, and now we're going to go into the model development. All right. So this is where it gets even more technical. All right. So, try to follow along. I'll try to explain things, very simply and all that. Cool. So model development. So first we got to do some processing on our model data frame, because down the line, we're going to have to do something called vectorization on our parts. And I'll talk about it when we get there, but we got to do some preparation first. So what I did here is that if you recall the event dex data frame, let me just kind of cut to it. I just kind of changed the shape of the data. Before, each row was a unique card, right? So, before any event dex, you might have like Blacklisted Soldier, and you have the card amount as 1, and then you might have the card name as Blade Knight, and then the card amount was 3. You wouldn't have 3 rows with Blade Knight because you had the card amount specifying the amount of card name in that deck, right? But in this case, I've actually exploded, it's kind of the term, I exploded the card name by card amount. So now it looks like I have Blacklisted Soldier, 3 Blade Knights, and Breaker. And again, this is just some pre-processing steps once you get to vectorizing the card names a bit later. And I'll talk about what all that is once we get there. Just want to say that we changed the structure of our data. All right. Okay, so train and test split. All right, so whenever you are training your model, what usually happens is that you would create this training and test split of your data. And in that way, in your training data, you would train your model with that data, you would do your cross-validation on the training data, and then whenever it's time to, once you have your model pipeline, ready to go and ready to test out of sample, then you can look at your testing data, your out of sample data, and see how your model performs. This is to avoid overfitting, all right? All right. So train and test split. So the way I'm doing train and test split here is a bit different from other model workflows, and that's because we're going to have an augmentation step right after this step. But let's kind of just look at the code first. Okay, so train and test split. So we have our decks. I'm going to be splitting that up by an 80-20 split, where 80% of our decks is going to be on our training data. That's what we're going to train our model on. And then 20% is going to be in our testing data that we're going to test on, all right? And we're going to do that by the URL, which essentially operates as our deck ID, because each deck has a unique URL, all right? So we're going to be splitting by our URL, and we're going to have a 2080 split here. Test size is 20%. We're going to set a random state here to make this reproducible. Don't worry about that. And a very important step here is that we're going to stratify this split as well. What stratify means is that we have imbalanced classes, right? We have like 600 chaos turbo decks, and our lowest samples is filtered for 5. So we have, class samples that ranges from 600 to 5. And whenever you're doing these splits, you don't want to do it randomly. You want to make it so that each deck class is represented proportional to, its representation in the deck. All right. So this makes it so that each split here in train and test, each deck class is represented in them, proportional to the 80-20 split. Cool. All right. So now we've split our decks into our train and test, URLs or deck IDs. And then with those URLs or IDs, we're going to create our train and test data frame. So this actually has our decks in here. All right. And we can see here that in our training data, we have 1,200 decks. And in our test data, we have 300 decks, that 80-20 split. All right. Cool. So we're about to talk about data augmentation. And the reason why I've split it by deck ID, because alternatively, what people would do is that they wouldn't split it by ID, they would just split the data frame itself. And you basically do the same thing. but with the data frame itself. And the reason why I've split the URLs or the IDs instead is because I'm going to be creating copies of each deck. All right. In our training data, I'm going to create up to 5 copies of each deck because we're going to augment those copies. And what that means is that for each copy, I'm going to randomly remove cards from it so that it has a certain partial level. What that means is that, say I have, all our decks currently are full decks. They have a partial level of 100%. 100% of the cards in the deck is in our data set. We have full decks right now. Whenever I want to start using this model out of sample with, cards from replays, I'm not going to see 100% of the deck all the time, right? I might see like 20% of the deck. I might see 40, 60, 80, etc. All right. The point of data augmentation is try to make the model a bit more robust to partial decks, basically. And to do that, I'm going to be creating copies of each deck, and I'm going to be creating copies at different partial levels. So I might create, so for one deck, I'll create a copy that has 20% of the cards from that deck. Next one, 40%. Next one, 60, 80, and the 100. So I'm creating copies of each deck, up to 5 copies at different partial levels. And if I were to have done augmentation before doing the train and test split, then what might happen would be I might have the same deck in both the train and test sets because they're copies, right? And I'm doing this random split, but I'm not splitting by the deck IDs themselves. Okay. So that was just a very important note when it comes to doing your train and test split, given the factor of we're going to be creating deck copies because we want to avoid leakage. If I were to leak a deck from our training set to our test set, the results would be biased. We would overfit. Okay. So this is the augmentation part of the notebook. Like I said, we're going to be creating partial copies of each deck, 20%, 40%, 60, and 80%. All right. And we're going to augment our training and test data sets. And what we're going to be left with is now, basically these data sets are multiplied by 5. So now we have 6,000 decks in our train set and 1,500 decks in our test set. And, these are partial copies. So now we have representation of decks that might have 40%, again, 20% of cards, 40, 60, 80, and 100% of cards in those decks. Great. And they're also split by the deck ID, so there's no leakage, all right, between these train and test sets. All right, cool. All right, so now we're going to get into that vectorization stuff I was talking about a bit earlier. So, of our decks, the thing that we're trying to predict the deck type on is by the cards. In other words, the cards is our feature. All right. The cards are our feature. Given cards, I want the model to predict the deck type. But the model does not work with, card names. It does not work with strings. All right. I need a numerical representation of that string so the model could understand value, and try to assign importance on these cards to predict deck types. And that's what vectorization means. It's going to be taking these card names, giving it a number so that the model could use that to predict deck types. All right. So in vectorization, there's different methods, right? The very basic one would be one-hot encoding. You might have TF-IDF, which is what we use here. You have bag of words. You have embed methods, all right? So the first vectorization method that I kind of want to talk about just to kind of explain the process a bit more is the one-hot encoding, because that's actually the first one that I've used. And I'm actually going to show you what that is right here. So let me close all this. Let's look at one-hot encoding. All right, so here's an example of one-hot encoding. So you can see here that this would be our data. All right, you can see that food name will be our card name. This would be like Black Luster Soldier, Thunder Dragon, Chaos Sorcerer, right? But what one-hot encoding does is that it changes this data frame here so that these card names are now columns. So this is now our Black Luster Soldier, Thunder Dragon, Chaos Sorcerer. And what one-hot encoding does is that whether this apple is present in this deck class, which I guess this is you can see here that they have here as 95. If it's present at 95 calories, to put it as a 1. Otherwise, put it as a 0. So for 95 calories, you can see that it's only apple. So what it does here is that apple is 1, is present, chicken 0, broccoli 0. All All right, likewise for 231 calories, likewise for 50. So this is how it would change these card names to have a numerical representation, right? But there's some issues with one-hot encoding, and that is that it doesn't account for frequency. What does that mean? Let's say that I have multiple apples here at 95. One-hot encoding only assigns a 1 or a 0 whether it's present. So in the case of Yu-Gi-Oh cards, if I'm running 3 copies of a card, it's not going to care for that. Only whether that card is present in the deck, right? So that's a dimension that one-hot encoding wouldn't count for, right? And then there's also another issue with vectorizing, which is like, you can see how each feature has a column, but this is only defined by the features that it knows of, right? So apple, chicken, broccoli has 1s or 0s. But if a new food name came into here, like, I don't know, beef, say beef came into here, it wouldn't have values for these. So each vectorization method is going to have different ways to deal with all of these problems. Well, let's think about it in the context of our own problem, which is we're trying to predict deck types with cards. And the number one problem with one-hot encoding was it doesn't account for frequency. Okay, but hopefully we kind of see now how the numerical representation of these texts or cards would be done. Typically, you're just taking this data frame that we have here and just transforming it to kind of look something like this. That's kind of what all of these vectorization methods would do. It's just a matter of which method that you're using, how it would assign a value, what that value is, how it's calculated. All right. All right, cool. So that's one-hot encoding. That's kind of how vectorization kind of works. And the method that we actually end up using is called TF-IDF. TF-IDF is the vectorization method that we use, and what it stands for is term frequency, inverse document frequency, I believe. And the cool thing with TF-IDF is that it does account for frequency. We'll talk about that in a moment, in the name as well, term frequency. And the cool thing about TF-IDF is that it attempts to value the importance of terms in a class within and across classes. So basically what that means is that, say this thing is accounting for term frequency or class or card frequency. So it's looking at Chaos Turbo. What is the most frequent cards in Chaos Turbo and trying to give a high value to that for Chaos Turbo and trying to use that to predict Chaos Turbo. You know what kind of cards you will see at the top? You might see a lot of cards that Chaos Turbo, tends to run, like Thunder Dragon and all that. But you would also see is staples, right? You'll see like Pot of Greed, Charity, all that. And what TF-IDF does is that through both this TF, term frequency, and IDF, inverse document frequency process, it would actually balance out how frequent a card is across classes, but also it would balance that out by whether other classes also have that card. So essentially, if that card is a staple across many classes, it would kind of weigh that down a bit more. So what TF-IDF is trying to do is trying to find the most important card for a deck class. And it's kind of an indirect, or it's kind of a good way to address staples, more or less. All right. So those are some of the differences with TF-IDF and one-hot encoding and some of the useful applications for it for our specific problem of trying to find cards that have the best signal to predict a deck type, accounting for stuff like staples. And we'll actually look more into this a bit later. I have demonstrations of all of this that, hopefully y'all could follow along with. All right. So here we go. So number one, first of all, when we try to do vectorization, we got to transform our data a bit more. And so what we have to do, I'm not even sure if it's useful to mention this, but recall how the data looked like before. Our data looked like this, right? It had a Black Luster Soldier, it had 3 Blade Knights here, right? There's no more card amounts here. And this was a step necessary to do the vectorization. And what I mean is, what we're now going to do is that for each deck and each cards in these decks, we're going to concatenate these card names by a separator. And this is what it means, actually. What it means is this, all right? So I've kind of nested the card names into this one row here. You can see that this is a list of, Graceful Charity. You see right here? You have Graceful Charity. Right here will be Mirror Force. And then it'll be the rest of the cards in that deck. And if there's duplicates or ratios greater than 1 in that deck, then this card would be in this list multiple times. So it might be like card destruction, Dekoichi, and then another Dekoichi, right? All right. So what we're doing is that we're taking this list of card names and we're going to concatenate them into one string. So this would be Graceful Charity. And we have this separator, this pipe separator. Then there's Mirror Force, another separator, and so on and so forth. And this concatenates the card names into one string or like one paragraph, let's say. The reason why you have to do this is that, typically when you use TF-IDF for other kind of modelings, let's say I'm trying to model the news, right? I'm trying to model the news to tell me if, it is likely, okay. Let's say I'm trying to model the news and I have like paragraphs, I have article, I have text from the news. And I have text from the news and I'm trying to predict whether or not this text would indicate that, earnings for a stock would go up or down, right? So I would give it paragraphs of text. And what this vectorizer would try to do is that it would try to break up this paragraph into terms. It would break it up into terms or words, and it would assign values to those words. What would happen if you don't specify a separator, like a pipe, between card names is that the default behavior for the vectorizer is that it would take this paragraph of words, in our case, this paragraph of card names, and it would have a default separator of a space. And what that means is it would treat black as its own word, essentially black as a feature. It would treat black as a feature, luster as a feature, soldier as a feature. And it would assign values to, how often these terms or cards or whatever is represented amongst all the other stuff. So you would see, you would see high frequency for things like, the and, and, is, of, stuff like that. Stuff that is kind of like the staples in our examples, right? And not only that, but, those kind of splitting up the card names in that fashion is not very useful when it comes to trying to, because these card names has importance, right? All right. So that was an explanation of some of the transformations that we had to do to prepare our card names to be vectorized. And that is to concatenate them by a consistent separator and specifying that separator to our vectorizer here. You see, TF-IDF vectorizer, our token pattern is going to be this regex where it's going to look for this pipe character. And it's going to split up this card name string by this pipe, and it's going to assign values to each card. All right, it don't just come out the box like that. You got to do this processing step first, and that way, once TF-IDF starts assigning values to terms, it would actually assign them correctly to the full card name. Great. All right, so that was a processing step there, and then it's going to take in that card name string that we were just discussing. It's going to take that in. It's going to do that transformation, assign those values. And then after that, there's this label encoding step, which basically means you see this deck class they're trying to do predictions of our target variable. This deck class also has to turn to a number. So it's not very important to know, but basically like Chaos Turbo might be 0, Warriors, 1s, doesn't really matter. All right. Just know that all text, all strings is going to be turning into numbers in some form or another. Cool. So that's the vectorization step of this pipeline. But I want to go a bit further here. I want to, further show y'all a demonstration of this TF-IDF vectorizing and how it's assigning numbers to cards in a practical example. So I have a plot here. All right, so I'm just going to scroll down to the plot first. This is the plot. We're going to first be looking at the term frequency of values of cards in Chaos Turbo. So first, let me scroll up here and actually just go down line by line what's happening. So first, we're going to be looking at the deck class of Chaos Turbo. All right, that's our selected deck class of Chaos Turbo. All right, so we have our selected deck class of Chaos Turbo. We're going to filter down our training data for Chaos Turbo decks. We're going to assign our TF-IDF values to each card, given the configuration that we did prior with the separators and the pipe and all that. Then after we do that, we're going to do the same kind of process for IDF, and we'll talk about IDF in a separate chart, in a separate plot. But more or less, the most important thing to know here is that this chart shows the top 10 term frequency values for Chaos Turbo decks in our dataset. So this is top 10. This is bottom 10. These are how the numbers are assigned. All right. So let's look at the top 10 term frequency values for Chaos Turbo. The number one most frequent card in Chaos Turbo in our data set is Thunder Dragon. This has the highest value. And the reason why it's Thunder Dragon and not like, Pot of Greed or Charity, why you might not see those cards in here is because remember, our training data has been augmented, right? So it's been augmented so that there's different partial levels in our data set. So we have decks that's only 20% of the deck, 40, 60, 80, 10, or 100. So the cards that are played the most or that has the highest ratio is more likely to be seen across these decks so that these cards that are also likely to be seen very frequently in these classes, in this case Chaos Turbo, but also played more than Pot of Greed due to the ban list, obviously. It'll be number 1 here. Okay, so that's why you see Thunder Dragon up here number 1. All right, then you got Spy, the Koichi, Fate, Chaos, whatever. So this is literally just looking at how frequent these cards are in Chaos Turbo and assigning a value to them. Okay, most frequent cards in Chaos Turbo up here. And bottom 10 is the least frequent. So you can see the very least frequent card here is Injection Fairy Lily. And you got Newdoria, Visor, Toon Cannon. So this is probably a mislabeling with Chaos Turbo and some kind of combo deck. Then you got Dark Magician, Stein, Trunade, Black Illusion Ritual. These are definitely mislabelings, but they're so infrequent that is making it down here at the bottom 10 term frequency values. Okay. So that's term frequency. That's how it works, given a practical example of Chaos Turbo. So these are the most frequent cards in Chaos Turbo. But you can't just quite take this and try to predict Chaos Turbo decks whether or not it has these cards. Because it doesn't, again, it doesn't balance out for staples. There's a better way to try to deal with that. Okay. And the way that it does that is with IDF. So IDF is the second part of that vectorization process, is a separate formula. And what IDF does, inverse document frequency, is that TF right here, term frequency, looked at the deck class of Chaos Turbo, right? And assigned values for Chaos Turbo. What IDF does is that it looks at all deck classes, Chaos Turbo Warrior, Warrior Turbo, all that. It will look at all deck classes and it will look, one second. And yes, so it would look at these deck classes and see which is the most frequent across all deck classes, right? And the reason why it's doing that is trying to find out which ones are not very significant to determining whether or not a card is Chaos Turbo. So if you look at the top 10 and bottom 10 for IDF, if you look at the bottom 10 cards here, or the bottom 10 values here for IDF, these are the staples, right? So the number 1 bottom card that a lot of decks tend to have is Nobleman of Crossout. Then you got Graceful Charity, Pot of Greed, Ring, Heavy, Snatch, Breaker, Delinquent. These cards are in many deck types, not just Chaos Turbo, right? Magician of Fate, those control decks, flip control, some warrior, flip warrior decks, right? So these cards are not very significant to whether or not Chaos Turbo is Chaos Turbo. Okay? But here are the top 10 cards. And these are just very kind of rare cards that, might have significance for whether or not a card is Chaos Turbo. This is not very important because, kind of disregard this. The ones that's really important here is the bottom 10. And what happens between TF and IDF is that they balance each other out so that it tries to tell you what is the most important card for Chaos Turbo, to try to predict Chaos Turbo. Likewise for any other deck classes. Okay? It's kind of a way to balance out frequency with whether or not it's like a staple or something. Okay? All right, great. So I hope that was, I hope y'all kind of understand how the numerical representation is happening for the cards and the method that's being used here, TF-IDF. All right. All right, so now we're going to continue down our model pipeline, and now we're going to get to the actual training of our model. The first thing we're going to do is try to handle class imbalances. And recall what I said a bit before, our data set obviously has a big imbalance in classes in the sense that Chaos Turbo has the most, and it could go down to 5 samples of a separate deck class. Okay, that's a problem when it comes to modeling. And so there are some things you could try to do about that in modeling. They're not very popular things to do. I think it's kind of controversial as well, a lot of these methods, because all of these methods, more or less, it's just going to multiply the classes with lower samples to hit some threshold. More or less, all of those methods, that's what they do, right? Whether or not you're doing something as simple as a random oversampler, as we have here, or you're doing something more complex like a smote, where you're interpolating new deck classes based off of similar deck classes, right? So just to kind of describe the range of methods that you could use here, I'm using a random oversampler. What this does is that, you know, look here in this table, I have the deck, I have deck classes here, Chaos Turbo Warrior, Chaos Control, so forth. And I have the number of samples for these deck classes in my training data set. So our number one is 2400 Chaos Turbo, and recall these have been augmented, right? So 1600, etc. What this random oversampler does is that it would look at which deck class has the most samples, and it would just multiply every other classes until it hits the sample of the highest sample Chaos Turbo randomly. Okay, so it will multiply things randomly within each classes to hit the same number of samples as Chaos Turbo. Now, obviously, that sounds kind of sus. Just multiplying shit. I don't know. It's kind of sus, and it's also kind of unnecessary for decision tree models as well. They can kind of see through this from what I read. So this is one way you could go about it. You could just randomly oversample classes up to a certain point. You could also do this so that you could kind of control for how much you want to multiply for. Say you want to multiply up to 600 classes minimum each. And then you have techniques, methods like smote. And what smote would do is that, say I have warrior here, and I'm trying to increase the sample. What it would do is that it would look at other warrior classes, and it would take cards from those warrior decks and just randomly create a new warrior deck off of it. And I'm not sure what kind of deck it would create off of doing something like that, so I didn't really do it here. And that combined with the fact that this is kind of controversial and not really effective anyways, I just did the simplest oversampling technique here, which was just to do a random oversampler, default settings, and just let it run. So in this modeling, I've tried with and without this step, and it didn't make a difference. Okay, so I'm just having it here just to kind of talk about some class imbalance handling and some stuff that I've tried, but moreover, it didn't really matter this step when it comes to the overall performance of the model. Cool. All right, so now we're going to get into cross validation. All right, so recall we have our training and test data set. Okay. What cross validation is that, first of all, recall we're training our data on the training data set. So we're only talking about training data set right now. All right. So we're going to use our training data set to train our model. And what cross validation does is that we could define a number of folds and split up our training data set by that much folds and, create multiple train and test split iterations. All right. Example. Say I have 2,500 decks in my dataset. I have 2,500 decks. What this cross-validation would do is that if I want to do cross-validation on 5 folds, what it would do is that it will take that 2,500 decks and split them up into 5 random folds of 500 decks, 500 decks, 500 decks, 500 decks, right? So I have 5 folds of my training dataset of 2,500. So now I have 5 folds of 500. And what it would do is that it would iterate throughout these folds, where it'll be like, 4 folds is the training set, and then it'll hold back 1 fold as a test set. And it'll just randomly go throughout all those folds, and it will just create new training test sets off the data, right? So it's just repeating this training and test set exercise with our overall training data set of 2,500 sets, okay? So that's what cross-validation is. I'm just splitting up my training data set further, and it's doing this cross-validation, and it's doing all this modeling with different training and test sets, different subsets of our training data. And what it would do is that it would kind of aggregate the results and give me the best results that my model has performed on with the training data. So that's kind of the goal here. It's just a robust way to avoid overfitting. Okay, that's what this is. So we have a training data set. I'm going to split it up into folds. I'm going to do iterations on them to try and train and test it on it, as much time as my PC can handle, and at the same time, while it's doing all of that training test split multiple times, with a number of iterations, well, what we could also do is something called hyperparameter tuning. I'm not going to get into depth with this. I have a section kind of explaining it, but what it means is basically in this modeling, you could give it inputs, and these inputs are like configurations. All right. These inputs, depending on my data, depending on the kind of modeling that I'm doing, a certain input like max depth might have an optimal number for my model, for my data. And since I'm doing this cross validation so many times, I'm doing this training test set so many times. What cross validation can actually do is go through each parameter here in these hyperparameters and pick out which one best worked with my model and the data. So that's kind of the high level of what it is, but just think of it as like, given all these iterations, it's trying to find the most optimal settings for my use case. All right. So I'm not gonna go over each one of them here, but they all control something different for XGBoost models. And over here, we are initializing the XGBoost model as well. Objective is multi-solve probability. What that means is that for each deck type prediction that it does is going to assign a probability to it, a confidence. Number of estimators, I believe, is the number of trees. Random state to make this reproducible. And the number of jobs, this is a CPU thing because modeling is very CPU heavy, especially when you're doing cross-validation. Here's our random cross-validation method or class here. We're going to give it our model that we just made, our XGBoost model. We're going to give it our hyperparameters. We're going to specify the number of iterations, the number of folds, number of jobs is again a CPU thing, random state, make it reproducible, and then the scoring, how accurate the model is. All right, cool. So now we've initialized our model and we've initialized our cross-validation classes. So next thing we're going to do, we're going to give now our cross-validation, we're going to fit it with our training data. So this is our X trained oversampled, Y trained oversampled, don't worry about it. More or less it's just, we're giving it our training data now. It's time to actually find out which fold had our best estimator and then pull that out as our best model to then start doing some out of sample testing, okay? All right. So this takes a while, depending on your PC and all that. And once the fit was done, I have my best model here, my best performing model on the training data. And now my best model is here. And these are the parameters for the best models. I have a section here about how the cross-validation curve changes. Because recall in this hyperparameter distribution that we have here, for maximum depth, I want a cross-validation to test maximum depth of 5, of 6, of 7, of 8. Find out which one of those is the best settings for the model. And this is kind of showing that curve, right? So you can see here parameter max depth. It goes from 5, 6, 7, 8. And this y-axis of mean test score goes from 0 to 1. So you can see that it's already it already hit a high point here. If I were to have had a lower maximum depth here of like 4, 3, 2, 1, I might have seen a curve here where the idea is you would kind of wait to see at which number the curve would kind of plateau, and then you would try to get that number and use that as your settings for your model. All right, so don't really worry about that, but that's just a step. And the reason why I'm going into the depth that I am for some of this is that it's not just for people to understand what went into the model, but if you're trying to do this yourself, I'm just trying to explain pipeline, what I've been through, and these processes, right? All right, cool. All right, cool. So now we have our best model from our cross-validation, right? So we have our best model right here, all right? Best model. So we have our best model, and now we're going to see how it performs on our auto-sample data. We're going to give it our testing data, all right? So we have our best model. I want to predict now on our test data, and I want to get what my model predicted here, my Y predictions. And then I'm going to compare my Y predictions with what my model predicted with what the deck classes actually were from the test set. And I'm going to create this classification port. All right. So here is going to go over the performance of our model, basically. So let's take a look here. All right. So this was our model's performance. Okay. So on the left hand side here, this is the deck classes. Okay. So we have Bazoo, Cat with Decay. This is all of the deck classes. And these values here, we have precision, recall, F1 score, support, and down here we have like totals. We have aggregations of the performance of the model. So let's look at an example here. Let's look at Chaos Warrior Turbo. So Chaos Warrior Turbo has a 1 or 100% precision. What that means is that whenever there was whenever my model predicted that a deck type was Chaos Warrior Turbo, 100% of the time it was Chaos Warrior Turbo. All right. When my model predicts something was Chaos Warrior Turbo, it is Chaos Warrior Turbo. Okay, 100% precision. What recall is that of the test data, there might have been more Chaos Warrior Turbo decks that my model didn't predict as Chaos Warrior Turbo. So the difference with recall and precision is that whenever my model says it's Chaos Warrior Turbo, it is Chaos Warrior Turbo. But um, but whenever there's a deck class of like Warrior, and my model said Chaos Warrior Turbo, is incorrect. All right. All right. So I hope that made sense. Um, So what you would like to see is a good balance here between precision and recall, basically, because precision again means that whenever my model said it's Casper Turbo, it is Casper Turbo, and the idea between precision and recall is to try to avoid false negatives. Is basically the point. If I see something here of 100% precision and 100% recall, what that means is that whenever there was a Chaos Warrior Turbo deck in the test set, my model predicted it as Chaos Warrior Turbo and never made a mistake anywhere else. All right, but there could be cases where my model was correct every time it said Chaos Warrior Turbo, that a deck was Chaos Warrior Turbo. But there might be cases where the test set is saying that something's Chaos Warrior Turbo, but my model says something else. All right, all right, cool. And then the F1 score, they call it. It's like a harmonic average between precision and recall. So this is trying to like balance out these two values together to give me like a. They call it harmonic average, not the same as an average. Okay. So this is basically the performances of all the deck classes in our test data performance. And down here, we can kind of see the aggregate or totals of the performance. So here in accuracy, we can see that my model had a 91% accuracy. And the tricky thing about accuracy is that it's essentially looking at the precision. And it's also going to get kind of biased at which classes was represented the most. So we can see here that the most represented class type here is of Chaos Turbo. And it was my model was pretty good at it, right? It had a 96% precision and had a 98% recall. So, since this is the majority of the classes, the accuracy is going to be kind of, biased towards this deck class that it can perform really well at, although it is the majority of the samples in this data. So it gives you accuracy, but also gives you these other averages that tries to balance out how these classes performed. So the macro average, it would treat every classes equally, and it would average out all of these scores. Okay, so it would treat every class equally, and it will give you the performance of that. All right. So it would give me 68% if everything was equal. But at the same time, this next one here, the weighted average, what it does is that it would try to weight everything out equally. Oh no, it would try to average out the performance metrics on all the classes, not just precision. But it would do that in proportion to the number of samples in that class in the test set. So what that means is it's going to weigh the Chaos Turbo stuff a lot higher than the Chaos Recruiter stuff, just because there's such a low sample in the Chaos Recruiter. And this actually gives you a better representation of how the model will perform out of sample, because out of sample, Chaos Turbo is going to be the number one deck class in popularity and sample and all that. So in reality, if I were to bring this model out to the world, I would want to look at weighted average because it would actually look at the proportion of these deck class samples in the dataset. Okay. And one more thing that I want to mention about this performance report is that it says 91. It says 91. And what y'all got to remember here is that this is including augmentation, right? So this is including deck types with a partial, exposure of 20%, 40, 60, 80, 100. Even with deck types where 20% had an equal proportion to the other partial levels, it predicted 91% accuracy. And 20% of a 40 card deck is 8 cards. So only seeing 8 cards across these classes, with that kind of distribution, 91% accuracy. Okay. That's the performance score, or the performance report. So let's look a bit deeper into the performance of the model. All right. So I have like this aggregate performance on all these different partial levels. It's giving like this one number. But what I actually want to know is how the model performed at different partial levels, right? I actually want to know specifically how it performed. So what we can see here is that at a partial level of 20%, 40, 60, 80, and 100, here's how the model performed given that much cards. So at 20% partial level, my model has an 80% accuracy. For 40%, 90, 60, 95, 80, 96, and then it kind of plateaus. What you would like to see is that for this thing to go up till it hits 100, because once it sees 100% of the deck, it should know what the deck type is. But the reason why that's not the case here is actually because of some mislabelings in the training data. And I actually go into real depth on this here in the next notebook that I'm still going to cover in this video. Okay, so this video is going to be a little bit longer. All right, but if you want to know why it actually plateaued, it's because the training data has some mislabelings, and it's just not going to make good predictions if the training data has some inaccuracies, basically. Okay, so this is what the curve looks like across partial levels. And so this next one here actually shows a confusion matrix. And what that means is that you have this matrix here where we can actually see what my model is mislabeling. All right, so can I find patterns as to like what my model is incorrectly mislabeling for a deck type? That's what this chart does. So we can see here in the y-axis, this is the actual deck type from our test data, right? So you can see here for Chaos Turbo. For Chaos Turbo, this is the actual, in my test data, say the actual deck type was Chaos Turbo. And the y-axis, or the x-axis, is what my model predicted. Okay, so in the test data, the deck class is actually Chaos Turbo. What my model would predict is for three times, my model predicted Chaos Control for Chaos Turbo decks. 5 times, it would predict it as Chaos Return as a Chaos Turbo deck. The majority of the time, 631% or 631 of the time, my model predicted Chaos Turbo as Chaos Turbo. So ideally, you would only want to see values on this diagonal, because if it's on this diagonal, then my model predicted exactly what the deck type actually was in the test data. So Bazoo Return, etc., etc. Okay, but let's actually take a look at where confusions are happening. Okay, so Chaos Control, and recall this is with partial data. Okay, so we have Chaos Turbo here, and there's 3 times where my model predict Chaos Control. If you think about a 20% partial level of a deck, only 8 cards, there are some Chaos Control decks in Format Library where 36 of the cards is like a Chaos Turbo deck. And like 4 of the cards is like 2 Scapegoats and 2 Metamorphoses, right? They will call those like Chaos Turbo Control decks. They will be labeled as Chaos Control in Format Library. You have cases where 36 out of 40 cards in a Chaos Control deck is indistinguishable from a Chaos Turbo deck. So when I have partial levels of down to 8 cards, 20%, this is normal. This is what you expect, all right? So I have Chaos Turbo, 3 times Chaos Control, 5 times Chaos Return. Again, Chaos Return, they all don't look like Dingo Sing's deck. There's a lot of Chaos Return decks out there that is just Chaos Turbo, but with returns in it, And then you have Chaos Turbo, obviously. And then I got Flip Control. Flip Control, we'll see that in a second. All right. But that's basically how you interpret this chart. And that's basically where some of the confusions happen. That's why it's called a confusion matrix. Let's look at a common confusion as well with control decks. So whenever the deck class was actually Chaos Control, what did my model predict? All right. 121 times it predicted Chaos Control correctly. 4 times it predicted Chaos Recruiter, 11 times Chaos Turbo, and down here, Go Control 4 times. Control is another example, right? I have partial levels. I'm looking at control decks. For some control decks, between Chaos and Goat, the difference might be just Thunder Dragons and Chaos Sorcerers. So, and especially with Flip Control as well. Flip Control and Chaos Turbo, it can be very similar as well, especially when Chaos Turbo could play Mask of Darkness in his deck, thanks to builders like, Ghost Rider and whatever that plays these decks with Mask of Darkness and Solemn and all that. And we're actually going to look at real examples in the next notebook. I want to look at real examples here so that y'all can kind of see where the mislabeling is happening. All right, great. So that's the confusion matrix. This is all in the notebook if y'all want to look at this individually and see where the confusions happen. Just one more here. Chaos Warrior. Look at this, right? Chaos Warrior confuses 1 time as Chaos Turbo, 32 times as Chaos Warrior is correct. But down here, 11 times. 11 times it confused Chaos Warriors for Warriors. At partial levels, where the difference between Chaos Warriors and Warriors might literally just be 1 Chaos Sorcerer, it's a no-brainer. All right. And that's given the number of deck classes that I've actually tried to train on. I have like less than 30 classes that I've tried to train on. You know, there's one other I've seen someone else try to do this, right? And when I looked at their training data, they have hundreds. They have like over 100 deck classes. And these hundreds of deck classes, you might see like a deck class that's 5 different variations of a Bazoo DFT deck, right? Say you have 5 variations of a Bazoo DFT deck and it went under the rigor that this pipeline went through. If you are actually trying to predict at different partial levels, 20, 40, 60, 80, and all that, there's not going to be no difference between these variations of Bazoo decks of these 100 classes. Like the problem gets escalated even more, especially when you only have 9 samples on average per deck class. All right. So people trying to, I feel like there's an expectation as to how this model is supposed to perform. And I think it's based on something that wasn't under the kind of rigor that's supposed to go under. All right. It's a TLDR. Does not have the trained test split, does not have good enough sample, does not go through cross validation, does not have a comprehensive report of how the deck performed at different precisions, recalls, F1 score levels, does not actually have confusion matrix. It's missing all these things. All right. And this is what the model actually looks like. This is what the actual numbers would look like. This is the most confident I am with a deck type model in this field. The only improvement that I would like to, so I'm very confident with my model's pipeline. I like the vectorization method that I use. The oversampling, you could omit it. It doesn't really matter to me. I'll just kind of advise against smoke. And all the cleaning and all that was all good. And that pipeline overall was all right. All right, it tried to handle imbalances, try to handle partial levels. Oh yeah, the other part in the pipeline, you want to make sure that your model is robust so that it can handle partial levels of decks, especially when you're trying to train your model on partial data. Okay, you want to make sure it can handle all that. Great. So I like the pipeline. The only thing that I think could definitely use improvement is the training data, because the training data, again, it was very biased towards top performing decks. So I'm not going to see a lot of samples for Bazoo Return, Empty Jar, all of these decks that you would actually see in the real world. And also, there's just a mislabelings overall that would be nice to check. But that would require me having to manually go through a lot more decks or having to go through premium data from my library. And the issue with trying to go, well, the issue with trying to do both, say I get all the premium data from my library, and now I have a lot more samples for very like low performing decks. I have that, but now I still have to manually verify whether there's mislabelings. The mislabelings rate would just increase, and the effort it will take to manually verify things would also increase. So just kind of make things very inconvenient. That's the only improvement that I think I'll kind of make with this pipeline. I like everything I did here. Just try to improve the training data. All right, cool. All right, so in this next section of the video, we're just gonna look at these examples, right? All this part here is just loading in the model, bringing back in the data, all that. We're just gonna look at real examples here where my model made a mislabel on the actual deck type and see what happened there, all right? Cool. So I'm gonna brush through this. We imported some libraries, we queried the data. We did the same transformations to the data so that we could, do the vectorization. Actually, that's a bit later, but we had to transform the data, preparation steps. We did the filters, made sure that the deck classes had a minimum of 5 samples. And then we loaded in the model and the vectorizer that we used from the modeling notebook. All right, so we put in our label encoder, we put in the TF-IDF vectorizer, and we put in the XGBoost model. And then I created this helper function so that we could do some stuff. All right, here we go. Okay, so now this is looking at all the decks that we had from our event decks. So that's all 1,600 decks. Okay, so all 1,600 decks that I pulled from format library, I'm going to take those decks and I'm going to do predictions on the cards of those decks. Right now, obviously, 80% of the decks in there was trained on the model, so I don't really care about that. I just want to see that testing part, the test set that failed. I want to see what happened there, all right? So of the 1,600 decks that I've pulled from my library that I've done this whole modeling with, I want to see what my model predicted and what the actual deck type was. And I also want to have the confidence, right? So the confidence is a number from 0 to 1, and it shows how confident my model was in its prediction. So what this shows here is the deck URL. This is the actual deck in format library. And this is the actual deck that the format library says it is. And this is what my model predicted that deck to be. And this is the confidence level. So you can see for the first 4 samples here, Gravekeeper, 99% confidence. Great. Now I'm going to take this data frame and I'm going to filter for where the model predicted incorrectly. So of the 1600 decks, only 20 times did the model predict incorrectly given 100% cards of the deck. I haven't done any augmentation here. This is all 100% of the deck. This is the one that I want to see because ideally this would be 0. This is the thing that's stopping the model accuracy from being 96 to 100, right? So with the full cards of the decks, there's 19 occurrences where my model predicted something different from the actual deck in format library. And we're going to look at 10 of these. All right. Cool. And this is sorted by confidence as well. All right. So we can take a look at some of these here. The actual deck was Panda Burn. My model predicted Cloud Decay, Stein Monarch, Mataza, Flip Control, Chaos Turbo, so on and so forth. So let's look at these now. Okay. So we're going to start from the top down. So the highest confidence first, because ideally, in a perfect world, what would happen is when my model is presented with a deck class that it wasn't trained on, right? If it's presented with a deck type that it wasn't trained on, what I would like to see is the confidence to be low. Because in that case, I could set a threshold for the confidence and just say this is an other category or an unknown category, right? But if my model is predicting something at a 99% confidence level, then there's something that went wrong in the training. So I'm going to start with the highest confidence levels first and see what went wrong. All right, model demonstration example 1. So this top example here, Panda Burn and Cat OTK. This is the example we're going to look at. Okay. If you click on this link, this is the Panda Burn deck on format library. If you look at this, it has some cat stuff in here, right? It has cat, it has Last Will, Stein, right? It has these things, but it also has Panda Burn stuff, right? It has barrels, the trios, the floods, some more burn cards, Panda itself, right? So there's like a mix of these things. So it has cat OTK elements, but also Panda Burn. Let's see if the inclusion of Panda Burn cards had to do with the mislabeling. So what I did was I looked at format libraries decks, and I looked when they labeled a deck as Cat OTK. So I'm looking at Cat OTK decks from format library, and I'm looking to see if there's any examples of a Cat OTK deck that had Trio and Secret Barrel. And there was 10 results. And when I clicked on one of these results, this is a deck from format library that they've actually labeled as Cat OTK. And these have a lot of the same elements here. It has Cat, Stein, it has the Will, the burn cards, but it's labeled as Cat OTK. When my model is given training data where all these, features have the same, elements with Cat OTK and Panda Burn, that's where confusions happen. All right. That's the first example. So in the second example, this is actually the only example where it probably wasn't a mislabeling. All right, so let's take a look at it. So when the actual deck is Stein Monarch and the predicted deck is Mataza Rush, let's look at it. So this is the deck. So Stein Monarch, I've kind of deduced that it is whenever a deck has at least one Stein card, some Monarchs, and Last Will. Usually you might see this with Decree or with a Cold Wave, but it has those core cards. The rest of it, it's kind of whatever. It's kind of hard to define. Okay. So this is what format library is calling Stein Monarch. This is the actual deck. And my model predicted Mataza Rush. And it's predicting Mataza Rush probably because Mataza is in here, and probably because Mataza is such a strong predictor of Mataza Rush that it just made the misprediction. So, unlike other cases, I actually couldn't find a Stein Monarch deck that has Mataza outside of this card. Or rather, I've gone through both Stein Monarchs and Mataza Rush decks, and I couldn't find other examples that, had the same thing and where, confusion might have happened. All that I've seen was that for Stein Monarch decks, there's only one occurrence that played Mataza, and it's this one. So, I think it was just an example of, the model making a misprediction, Mataza just being such a strong predictor of Mataza Rush that this happened. All right, so let's go through the other 8 examples here. All right, so the actual deck is Flip Control. Predicted deck is Chaos Turbo. All All right, so this is the flip control deck from Format Library. You know, looks like a Chaos Turbo deck. The main features that could be causing the mislabel is between Mask of Darkness and Solemn. I've already done the filter if for all Chaos Turbo decks from Format Library that contains Mask of Darkness, and there's 26 decks. All right, so a lot of decks play Mask of Darkness and Chaos Turbo in Format Library. But let's see if we could push it further to see if there's any Chaos Turbo decks that plays 3 Mask of Darkness, because maybe the frequency of that card could be causing a mislabeling. When you look at this, you have one result here, and check it out. There's this Chaos Turbo deck with 3 Mask of Darkness, 3 Solemns. It's pretty much 38 cards, the same cards as this one, but this one's called Flip Control, and this one is called Chaos Turbo. So that's a mislabeling. All right, next one, Chaos Control, Chaos Recruiter. So check this out. This is a Chaos Control deck in Format Library. And Chaos Recruiter, if you don't know, is a deck that doesn't play Scapegoat meta, but it plays Tomato Angels and Chaos Sorcerers, stuff like that. Flips, Assuras, swaps. All right. Format Library is calling this Chaos Control. It might be calling it that because it techs the Scapegoat and meta, but it definitely has a lot of Chaos Recruiter elements in here. So let's look at Format Library for any Chaos Recruiter decks that play Scapegoat, because I feel like between Scapegoat and Metamorphosis, those are probably the cards that is making that label for this to be control. And when I do so, there is actually a Format Library deck that's labeled as Chaos Recruiter that plays more Scapegoat and meta than the one that's labeled Chaos Control, right? So this is a mislabeling. This is called Chaos Recruiter, despite playing the control cards, the same control cards that this deck plays, but it's being called Chaos Control. All right, mislabeling. Example 5, Flip Warrior and Warrior. This is an interesting one. So Flip Warrior, I'm not really sure what the definition for this is, whether or not it plays 2 Dekoichis, whether it plays 2 different kinds of flip with Dekoichi and Fate, whether it plays, more copies. I don't know how much flips is something ended up being called Flip Warrior. But in this case, that it made the confusion. This deck plays 2 different kind of flips, Dekoichi and Fate. All right. So I look at Format Library, I try to find Warrior decks that plays Dekoichi and Fate. And I got these 4 results here. All right. And when I look at one of them, here we go. So this is one Warrior deck from Format Library that plays both Dekoichis and Fate, but it's labeled as Warriors. Okay, so mislabeling. Example 6, Stein Monarch, Urk Beat. All right, this is the Stein Monarch that my model made the mistake as Urk Beat. You can see that it still plays the Stein, the Monarchs, the Last Wheels, but it also plays some of these Earth elements. You have Rat, Gigantes, Lily, stuff like that. Now I looked for Earth Beat decks from Format Library that contains Zabord. And when I did, I found a deck with the same elements of the Stein Monarch deck that it made the confusion on. So this is labeled as Earth Beat in Format Library, but it plays the same, Stein Monarch elements. It has the Stein, the Monarchs, it has the Last Whales, but also has all this other shit. It's labeled as Earth Beat. This one is labeled as Stein Monarch. Mislabeling. Example 7, Chaos Warriors, Chaos Recruiter. All right, this is Chaos Warrior. I found an example here called Chaos Recruiter. It's the same deck. This is actually the same deck. So this deck is labeled as Chaos Recruiter. This one is Chaos Warrior. I'm going to cause confusion, obviously. Example 8, Relinquish and Chaos Turbo. This is an interesting one. There's a case in Format Library where a Relinquish deck was mislabeled as Chaos Turbo given 100% of the cards. So let's take a look at that. So this is the Relinquish deck that my model made the confusion on. My model thought that this deck was Chaos Turbo. In Format Library, this is the Relinquish deck, right? All right, cool. And this is an actual Chaos Turbo deck with Relinquish. So this is, this is labeled as Chaos Turbo, but it plays, I think, it plays the same deck. It's the same deck, I think. Yeah, so this is the same deck. This one's labeled Relinquish. This one's labeled Chaos Turbo. So that's another example of mislabeling. Example 9, Go Control and Flip Control. So look at this one. This was also kind of interesting. In Format Library, this deck right here does not play Scapegoat or Meta, but it's labeled as Go Control. So that's kind of a big one. Usually stuff like that is strong predictors of control, but now not so much given the training data. But my model predicted this as Flip Control. I'm not sure if you could argue, because it has like a lot of tribute cards here. So like you have like your Air Knights and you have your whatever this is, your Blowback Dragon. So you have some tribute elements here, which kind of, but it's not monarchs. So but at the same time, you have all of this flip control stuff in here. So it feels like flip control, but that tech some tributes, in my opinion. But then you also have brand control here. So I don't know, something between Monarchs or flip control, I could buy it. But I think labeling this as flip control is a lot more justifiable than labeling it as go control. All right. So that was a case where I thought my model did a bit better in labeling this than the actual training data. And then that's it. All right, cool. So we went over 10 examples. I skipped one of the examples because it was a similar example that we've seen before with flip warriors and warriors. So we went over basically 10 out of 19 incorrectly labeled decks from thousands of decks. We only went over predictions on full decks because we will see the same effect being, okay, yeah. So all this was done on full decks. The reason why I didn't augment things to 20, 40, 60, 80 is because imagine the confusion that we've already seen. Now imagine only seeing 8 cards of a deck. You know, in general, you're going to see these kind of confusions, right? Chaos Turbo with flip control. You know, say I've only seen 8 cards of a 40 card deck. Chaos Turbo is going to be confused with flip control, chaos return, chaos control, right? Especially when the difference is a matter of 4 cards, 4 or 5 cards in the deck. Same thing with warriors. Warriors with flip warriors and chaos warriors, go control with chaos control, and panda burn. Given that you can't even distinguish panda burn with cat OTK with whether it plays panda burn shit. Big one as well. That's the reason why you would see big recall scores or lower recall scores in that classification report for these kind of deck types. It's for these reasons. So models are as good as its training data. Almost all incorrect predictions are explained away with mislabels in the data or low sample size. In some case, the model does a bit better than the training data. All right, so that was a big one. That was a very big one. And let me get out of here. So, I hope y'all now know what's going into the deck type model, how confident you can feel in it, and some improvements that you could make if you want to carry this on yourself, kind of reproduce some of this stuff and make the improvements that I've been suggesting. All right. So that's cool. And I'll catch y'all in the next video.